Thank you for the invitation. It's a pleasure to give this talk online. I don't personally like so much talking online, but I will try to do my best in this talk. I prepared this whiteboard instead of slides so that I can write on the whiteboard if you have questions, if you want some more explanations. So please interrupt me at any time. Okay, so let's start, yes, with the setting. In all the talk, X will be a smooth Fano manifold of dimension n, and the atom in this group will be discrete, and that means that this is the connected component of the identity. So this is sometimes is a necessary request, but in many cases not necessary, but will simplify some results. And there will be also some differential geometric part, so I need to fix a reference Kähler metric, a Kähler form omega in the first Tian class of X. Okay. So let me start with the introduction and with the motivation behind my work. Let me start with this main theorem. It's a theorem where many mathematicians have worked in the last 20 years, but let me just cite these guys. And this theorem represents a connection between a differential geometric object, like Kähler-Einstein matrix, and an algebraic geometric notion that is called K-stability notion. This one implies 2 and 2 implies 1, this equivalence represents, solves a very famous conjecture called the Tian-Donaldson conjecture on Fano manifolds. And as I wrote, produce a fascinating link between the differential algebraic geometry. In the talk, I will explain what Kähler-Einstein metric are, what is K-stability, and moreover, I will explain this delta bigger than 1, that is a valuative criterion to detect K-stability. For this first 5 minutes, let me just say that the importance of this theorem, because Kähler-Einstein metrics are objects that are studied in the last 100 years. Kähler himself, in the 30s, he introduced the now called the Kähler geometry because he was interested in finding this Kähler-Einstein metrics. So it's really a central object in complex geometry. In the last 20 years, K-stability becomes very important in algebraic geometry because it is connected to the constructions of moduli spaces and to singularities of the minimal model program. And this valuative criterion is very important to detect K-stability because in general it's difficult to understand which Fano manifolds are K-stable. We'll say more in the sequel of the talk. Okay, so let me first introduce this delta invariant. That is the easiest one to understand, to catch. Okay, so it is defined in this way. It is the infimum of over all prime divisors of all varieties that are above X. So you consider any Y that is smooth that dominate X through a isomorphism. So this is a partial order. And you consider all prime divisor E, and you take this infimum, where in the numerator there is the log discrepancy. So this is a measure of the singularity of E with respect to X of these prime divisors. While on the denominator there is this expected vanishing order. So it is a quantity that can be, is described by this integral. So it measures how fast the volume goes to 0 when you move to the direction of the exception divisor of the divisor E. To read this invariant in more classical terms, there is this remark where you can see this delta as some kind of asymptotic local annual thresholds, when for any m, you consider basis of this vector space, and you construct this divisor D that are Q linearly equivalent to minus kx, and they are given by this basis. And then you consider the infimum of this local annual threshold, and you let m go to infinity. So it is a measure of how much singular this particular Q-linearly equivalent divisors can be. It's a mutual singularity of the linear system associated to minus mkx, if you want. And recently, Aban and Zhuang have found a way to prove that this delta bigger than 1 is actually an efficient criterion to detect K-stability. But one problem is that you have to deal most of the cases. You have to deal case by case to detect which monomatic forces are K-stable. There are very few general theorems to detect K-stability. Some of them are given by these papers of Aban one. Okay, so if you have questions about this delta invariant, then I will go forward. I mean, we'll go back to this the last part of the talk, but just if you want K-stability, you can, for the moment, take this as definition of K-stability, delta bigger than 1. Okay. So in the next 5 minutes, let me concentrate a bit on Kähler-Einstein metrics. Will be a bit more analytic, but it will be necessary to understand the motivations behind my work. So a Kähler-Einstein metric is, as the name suggests, is a Kähler and Einstein metric. So it's determined by a Kähler form in the Friedstein class of the variety, such that it solves this Einstein field equation. So the Ricci of the Kähler form is equal to the Kähler form itself. Locally, the Ricci form is given by this formula. You write in coordinates omega as with respect to this matrix GJK, and you take the determinant of this matrix, and you have this Ricci form. This is important. This observation is important to understand, and then the Einstein equation can be translated into a complex motion pair equations. So to find Kähler-Einstein metrics, you need to solve these complex motion pair equations, where dV is a smooth volume form attached to X, while we look for solutions. This is important. We look for solutions that are in the set of Kähler potentials. So all U that are smooth, such that when you modify your Kähler inside the same cohomology class, you still have a Kähler form. Okay. So now I would like to spend 2 minutes about the idea behind the work of Chen, Donaldson, Sun. That was the hardest implication. So I mean, going from K-stability to existence of Kähler-Einstein metric, and this can be thought as a variant of classical continuity methods. So what they did, they fix a divisor, a smooth divisor in minus mkx. There is a typo here, and they seek for log Kähler-Einstein metrics. So they seek for omega t, that is given by omega plus I over pi the bar ut. So another Kähler form, another form in the same cohomology class of omega, such that ut is a Kähler-Einstein metric, determine a Kähler-Einstein metric on x minus d. So you solve this equation, Ricci omega t equal t omega t, and it is positive. So it's a Kähler form in this open set. And moreover, the potential ut is not smooth anymore. It is, but it's bounded and have some kind of cone singularities along the divisor dt that is given by rescaling your initial divisor d. Indeed, as you can see from the picture, the idea, okay, I cannot draw more than this. As you can see, you have your divisor d. You look for Kähler-Einstein metric that are smooth outside the divisor d, and along d they have some angle that depends on t. And when you move t to 1, you want to find your Kähler-Einstein metric. Of course, to perform this valuation, this continuity method, you need to assume K-stability. So K-stability is essential to perform this continuing method. Okay, so now if you look at this equation, globally, UT solves this equation of x. So we have this extra factor, this extra singular factor given by log of SD, where SD is a section that defines the divisor D. So on the right-hand side, we have some pole. So it's a singular, it's a degenerate complex motion pair equation, and the solution cannot be smooth. It's globally bounded, and it defines a singular metric of minus kx. So it's not a Kähler form anymore, but it is positive in a weak sense. But looking at this equation is important because now we can define this Vt as the sum of TUT plus 1 minus Tm log SD, and this is still in this set of singular metrics respect to omega. And moreover, you can check that solve this equation. So the important remark here is that we have the same equation, the Kähler-Einstein, the Einstein equation. So we are looking for some singular metric, such as the Ricci is equal to himself, but the solution has some prescribed singularity. I mean, the solution behaves as log of SD, some weight. So these are Kähler-Einstein metric with prescribed singularities. This was the main topic of my PhD. And the upshot of all this small digression is that in general, you can study log Kähler-Einstein metrics, but you can translate the log Kähler-Einstein metric into Kähler-Einstein metric with prescribed singularities. So this is a bigger set of special metrics if you want. Indeed, in general, you can do the same when you consider any y above x. So if you have a log Fano pair, y with a boundary by, so we have that minus ky minus by is ample, which it's enough that is nef, but let me assume ample for simplicity. And so that is above x means that the push forward of this line bundle is equal to the anticanonical line bundle. Then we can study log Kähler-Einstein metric above on y by directly below, and this is an important part of my work, directly on x, on the same on x omega, without changing cohomology class, but just asking some prescribed singularities. We can study all Kähler-Einstein metric on all y that are above x. So this is in line. This is in line with the minimal model program, if you want. So the main advantages are that the geometry of x is simpler, in general, and that, as I say, that we can compare the existence of log Kähler-Einstein metric, hence also a log k-stability notion above x, working directly in the same cohomology class as C1x. Indeed, let me say that there is a log variant of the Yau-Donaldson conjecture when this log Kähler-Einstein metric proved to be equivalent to a notion of log k-stability that is still important in algebraic geometry. And in many cases, to have this Yau-Donaldson conjecture, it is necessary to assume that the boundary by is effective. Here we don't assume that it's effective in general. Okay. So let me say the other questions that then let me go to. I will be happy if you have some questions about this first part. Okay, so it is natural now to ask if there is some kind of prescribed singularities that are algebraic, so that can be read algebraically. And if yes, we would like to have a k-stability notions directly on x that can be connected through a Yau-Donaldson conjecture to the existence of this Kähler metric with prescribed singularities. And also, if possible, a valuative criterion, that invariant. And more important, we want to study how K-stability behaves when one moves the prescribed singularities. So this is very the novelty. A really important novelty of the project is about checking how the K-stability notions varies. A priori, you cannot compare log K-stability for different this log Fano pair above X. Here, with this perspective, we can. Okay, so if you have any questions about this quick introduction behind the motivation to my work, I will be happy to hear. Okay. So as I said, the idea now is to define a K-stability notion on X minus Kx with respect to some prescribed singularities and connect it to the Kähler metric with prescribed singularities. And we want, of course, to relate this notion of K-stability with respect to prescribed singularities to known notion in algebraic geometry. Okay. So let's go to the main part of the talk. So from now on, we assume that L is minus Kx to lighten the notation. We recall that a Weyl B-divisor can be read in the Riemann-Zariski space, but for simplicity now, let me just say that it's a family of R divisors, such that the push forward of dy prime is equal to dy if y prime dominates y. An example is given by a divisor on X. You can define dy as the pullback of D, and this define a B-divisor. And in general, you can a B-divisor is said to be Cartier if there exists a Y such that any other incarnation of D on Y prime above Y is given just by pullback. So D is determined by Y, by dy. So we can now define this set as div Lx as the set of all generalized B-divisors. By generalized, I mean that countable sum is allowed, so they are not actually divisors, such that L minus D is nef. And this notion for, if you assume that D is Cartier, is equivalent to say that if I assume that D is Cartier at level Y, then this is equivalent to say that the pullback of L minus dy is nef. It produces a nef class. But in general, for Y divisors that are not Cartier, this notion of L minus D being nef is equivalent to say that for any Y, the incarnation L minus dy is nef in codimension 1. So, or if you want, nef Y divisor given by weak limit of Cartier nef divisors. This all in the Riemann-Zariski space. You can define some topology given by the projective limit, and then you can define nef divisors, nef B divisors. While the second assumption is just saying that this intersection, top intersection, that is defined as the infinite of the volume, these guys, because by the negative lemma, these dy are increasing, so this is decreasing. So this volume is positive. So we want that the class that are nef codimension 1 for any y are actually uniformly big. Okay. And why did I define this set of general divisors? Because actually this is the right algebraic description of a set of algebraic prescribed singularities that I was defined in my PhD, but it's more in terms of multi-body sheaves. I don't want to record it. But for the talk, it will be important that there is this one-one correspondence. So we want to connect now Kähler-Einstein metric with respect to this an element here to now there is typo div L to a notion of K-stability with respect to where we encode also this divisor, this B divisor D that is in this space. So now we translated essentially a natural set that it can be defined algebraically analytically actually in algebraic terms. Okay. So maybe let me just go back a moment. Let me just say this example to make more clear. If you take P2 and you consider 4 points, then you can blow up Y. You can blow up along these 4 points. If you consider function that is smooth and such that psi is equal to log of zeta squared around pi, when you take coordinates that are centered at pi, then a psi Kähler-Einstein metric, with this I mean a Kähler-Einstein metric with the singularities encoded by psi, is the same essentially as a Kähler-Einstein metric on Y. This is because this psi, what is called the singular psi, are encoded in the point P1, P2, P3, P4 with weight 1. So when you take the blow up, the boundary divisor that you hook up with is actually 0. So you can hook up with a genuine Kähler-Einstein metric on Y. So you can see also Kähler-Einstein metric on Fano variety that are above X can be read in terms of these prescribed singularities. Okay. Okay. So now we can define a K-stability notion with respect when we consider also this divisor D that is in this space. Let me first recall for some of you the usual notion of K-stability. So the K-stability is determined by some positivity on a weight called Donaldson protecting weight with respect to a set called of test configurations that is given the following way. A test configuration consists of a normal variety curly X, a flat and projective morphism to C, a C star action on the base that is the canonical C star action, and that lift to the canonical action on the curly X. And moreover, we need a polarized, a C star linearized pure line bundle over curly X. And we need that the general fiber is actually isomorphic to our polarized variety, and there is some degeneration when you go to 0. An example is the deformation of the normal cone. You take X times C, and you take the blow up of a point times 0, and you have an example test configuration. And in general, maybe let me write here. In general, you can embed your in general, you can embed your X into some Pn by minus mkx, and then you can consider one parameter group in Pn, and then this produces a test configuration Kähler X. So any test configuration, any ample test configuration actually is produced in this way. So you embed X in Pn, and then you take all one parameter group and you take the flat generation, and this is an ample test configuration. And yes, but the problem here is that you can embed for M. You have to consider test configuration for any embedding. So N can be very large. So you have a huge set of one parameter group to test. And the Donaldson-Futag invariant can be thought as a kind of Hilbert-Man for weight with respect to this one parameter subgroup. It's kind of degeneration. But there is a nice interpretation in terms of intersection theory. The Donaldson-Futag invariant can be defined in this way. Actually, it's a proposition, but for us it will be a definition. Can be defined can be defined in terms of intersection theory, where thanks to the C star action, we can compactify our test configuration Kähler X, Kähler L over T1, because the action at infinity is trivial. So we have this Donaldson-Futag invariant. And here, when I call uniformly K-stability, if you want the notion of K-stability, you have to ask that the Donaldson-Futag invariant is non-negative for any ample test configuration, and it is 0 if and only if Kähler X is trivial. That is the same as saying that Kähler X is isomorphic to X times C. But here we ask for uniformity K-stability, so we need that the Donaldson-Futag invariant dominates as kind of a norm of test configurations that is given by this functional, that exactly is a non-negative, and it measures the triviality of test configurations. And it is remarkable to say that actually last year, Liu Xiuzhuang proved that in general, uniforming K-stability under our assumption of the automorphism group is discrete, that uniforming K-stability is actually equivalent to K-stability. So there is no, we can concentrate on uniforming K-stability instead of K-stability. Okay. Any questions about K-stability, this notion? Okay. Okay. So the point now is that we want to consider this our divisor, our B divisor. So we need to interpret these test configurations in more Riemann-Zariski perspective. So the first observation is that this Donaldson-Futag invariant is a numerical invariant. Namely, depends on the first chain class of Kähler L. This intersection does not, it's a numerical quantity. So we can consider the following Riemann-Zariski space. We consider all Kähler X that dominate, C star equivalent dominate X cross T1. And we can consider the projected limit of all these Kähler X. There is a natural partial order. And we then can talk about pico dimension Weyl classes and pico dimension Cartier classes when we take pico dimension classes on Kähler X for any Kähler X. So these are cycles, numerical classes of cycles. And then we take the projected limit and we have these Weyl classes. If we take the inductive limit, then we have these Cartier classes. These two sets are endowed with the natural topology given by projective and inductive limit. But for our purpose, it's important to say that we can associate to the first chain class of L, where L is a test configuration. We can embed it in the one codimensional Weyl classes in this Riemann-Zariski space. So by Abuse notation, we denote by L. So the point is that we change perspective. Instead talking about test configurations, we talk about test configurations classes in this sense of numeric classes. This is very natural for our setting because we want to encode this divisor that is given in the Riemann-Zariski space associated to X. So in all Y that dominates X. So it is natural to try to change perspective in K-stability with this Riemann-Zariski perspective. And okay. So how can we encode the divisor D? Okay, we define this curly D, this class curly D, in the following as the class of the following B divisor. We need to define the curly D, curly X, the incarnation curly X of curly D to define a B divisor. So we pick curly X that dominates X cross P1, and by C star equivalent property, curly X over C star is isomorphic to some Y cross C star, where Y dominates X. And then if dy, the element of D at level Y, is given by this sum, then it's natural to define this curly D, curly X as the sum of AF curly F, where this divisor is just given as the Zariski closure or F cross C star with respect to the open bending of Y C star in X. This is very natural. The idea is actually maybe let me say choosing more things. So we have Y curly Y times C star that map into X C star. Then we have this curly X that actually maybe it's better to it's better to start with P1. Sorry. This curly X is a test configuration that dominates X cross P1, but actually over C star is isomorphic to Y cross C star. So when we consider this one, we have that D cross C star is here, and we just take dy, this curly X, as the Zariski closure of this divisor in curly X, component-wise. This is very natural because the idea is that the positivity to take under considerations are encoded in this class, numerical class L minus curly D. Indeed, this divisor can be thought as a fixed component that we need to remove from the positivity to consider. So as I've described before, when you have a local Einstein metric, this is a fixed part that enter into the game as a boundary. Okay, so the point is that with this perspective, the proposition definition is that we can actually, there exists a well-defined Donaldson-Kotak invariant. They are associated to test configuration classes, this Donaldson-Kotak invariant, and it coincides with the usual Donaldson-Kotak invariant when D is 0, and that's something that we want. And moreover, it is given in terms of an intersection formula, so it can be, in principle, can be computable. And moreover, actually, we have this kind of proposition when we interpret this Donaldson-Kotak invariant as an asymptotic local stability. Indeed, if we have a test configurations of x cross p1, we can consider y that dominates x cross p1, and we can complete this diagram to get a test configuration y for y cross p1. And what is the line bundle? When you pull back L, you must remove the divisor dy. So you have this divisor, this line bundle ly that a priori is just an f. And we have also this boundary that is given by dy minus ky x, the anti-canonical relative bundle. So it is the most natural line bundle to consider on y, on curly y, is this pullback of L minus curly dy. But a priori, this line bundle is not positive. It's not ample. It's not F in general. It's not big a priori. So we add some multiple of the center fiber, and we don't change the Donaldson invariant, because the Donaldson invariant is, we can prove that actually this is independent of the multiple m that you choose, if m is big enough. Indeed, in general, the Donaldson invariant is what is called translation invariant. And this can be, this Donaldson invariant with by is the usual log Donaldson invariant that is needed for defining log Kähler stability. So as we expected, this notion that we produce of Donaldson invariant is actually can be interpreted as a kind of asymptotic Donaldson invariant. And in particular, when D is Cartier, it goes back to the log Donaldson invariant. And as you can imagine, now we can define the uniformly D log K stability if there exists an A such that this Donaldson invariant dominates a measures of D triviality, that is JLD, that can be read analytically in a nice way, and it can be expressed always as intersection formula algebraically. And this inequality produce uniformity log K stability if you have this equality for any ample test configuration class. Okay. So before going to the main result, please again interrupt me if you have questions. I mean, I know that online it's difficult to to ask questions and so on, but please don't hesitate if you have questions at any time.
Everyone seems happy at the moment.
Okay. Yes. Yeah. Okay. So we can now go to the last part of the talk, that are the main results. Okay. First, I divided this theorem into a part that is analytic, a part that is algebraic. So let's fix L minus Kx. Let's fix the divisor D, that is a B divisor on this set of algebraic prescribed singularities, that is equivalent to fix a function that in this set that I didn't define, but that can be defined analytically in terms of multiple idea shifts. And this arrow produce one implication, the Yao and Donaldson conjecture in our setting. So if there exists a psi D Kähler symmetric, and I repeat, I mean a Kähler symmetric with prescribed singularities encoded in this psi D, then XL is uniformly D log K stable. So this is one implication of the Yao and Donaldson conjecture. Moreover, actually, we can prove more. Analytically, the existence Kähler symmetric can be described as minimizers of a certain functional on a metric space. I will say something more later. And this function is cursive. So this was done in my PhD. And we can connect now this cursivity to another notion, another algebraic notion that I didn't define because otherwise would have been too many notions. That is called the uniformity log Ding stability. The Ding stability is the K stability. The point also in the absolute setting, I mean without prescribed singularities, there is a notion Ding stability that is really important in the study of Kähler metrics. And it is really a notion that it's attached to the fact that L is the anti-canonical line bundle. Because you can define a K stability for general polarized variety in the same way as I did. But the point is that when L is anti-canonical line bundle, you can define also this notion of Ding stability that is more useful and more easy to study than the K stability. And I can prove both arrow here. So in particular, this already produced algebraic interpretation of Kähler metric in terms of D log Ding stability. We have an if and or if. And the point is that this uniform D log Ding stability implies the D log K stability. Okay. And what about the valuative criterion? I proved that actually this D log Ding stability can be read in terms of two stability thresholds, two delta invariant, delta D and delta tilde T. As we will see, this delta D is more known in the literature, but this delta tilde D seems quite promising and interesting. So this is the main result of my paper. I'm going to say 2 words about this delta invariant, about the proof, and so the main idea of the proof, okay, for this equivalence, the idea, okay, we want to study existence Kähler metric, so we perform a valuation approach on a metric space that is called A1. So it's a space of functions, of Trusiani functions, so a space of singular metrics on minus kx that are where the singularities are encoded by psi d. This is a complete geodesic metric space, and we can define a functional, the Ding functional, whose minimizers are exactly the Kähler metric. So the point is now is to prove this equivalence, is to prove that the existence Kähler metric is equivalent to cursive of this Ding function. And the point is that this Ding function is convex along geodesic, and you can prove that inequality. But this point of view is really this topology, this strong metric topology comes from this space. It's important also to prove that actually going from Kähler metrics to the uniformity log stability. Indeed, to any ample test configuration, we can associate a geodesic ray in this space. And the geodesic ray is algebraic because it is constructed starting from an ample test configuration. And the point is that the slope of the Ding functional is D. The notation too many D. Okay, but I didn't think about that. I didn't thought about that. Okay. The slope of this Ding along this geodesic recover this quantity that is the quantity needed for testing the Ding stability. So as you can see, if it is cursive, then this slope is positive. It's positive in terms of the J functional that is related to this D1 distance. So you get the Ding stability. So this is one arrow from here to here. And then from Ding stability to K stability, this relies on the fact that both notions can be described in asymptotic terms, as I did before. So I can use non-result strategies that are already in the literature that relies on, instead of Riemannian Zariski a Riemann-Zariski perspective that relies on a non-Archimedean perspective. So you can also read K-instability in terms of in non-Archimedean perspective, in terms of Berkovich unifications and so on. And okay, what about the reverse arrow? The reverse arrow, the point is, okay, as you can imagine, this delta invariant, the delta tilde, they need for a valuative criterion, so they need to be defined in terms of infimum of some quantities defined by infimum on with respect to some prime divisors, as we did before. So the point is to associate to any prime divisors, that is the infimum of this delta D, again a sequence of geodesic rays, a sequence of algebraic geodesic rays, and such that the Ding functional, this Ding function, the test configuration is continuous along these approximations. This is the same idea that had more or less the same idea that had Berman, Buxom, Johnson. But the point here is when you have prescribed singularities and when you want to read everything in a Riemann-Zariski perspective, you have many difficulties coming from pluripotential theoretical. From the point to read the Riemann-Zariski space, to do projection theory on this Riemann-Zariski space. Sorry. So there are many difficulties, but we can prove this delta bigger than 1 that is equivalent to delta tilde equal to 1. This is just from the definition we will see in one moment. And then from this delta tilde, we can go back to the coercivity. And this is for this arrow that conclude this equivalence. For this implication, actually, I rely on some recent result of Darvash-Zhang when I adapted the strategy. But again, the prescription strategies, there are many difficulties that I didn't expect in the beginning. Okay. So to conclude the talk, let me just say 2 words about these new invariants that enter into the game, that are easy to understand and that are more manageable than the K-stability notion. So for simplicity, let's assume that D is Cartier. So D is a divisor given on some Y, and such that this line bundle Ly is actually nef and big. So when you put back L and you remove the divisor dy. Then we have a log Fano pair, actually a weak log Fano pair because it's not ample but it's nef and big, but does not matter. So it is we have this line bundle Ly and this bundle by. Then we can define these 2 quantities. The first quantity is goes back exactly to the usual log delta invariant. So when this expected order, as you can imagine, is maybe let me go back one moment. Maybe no, let me write down. It's better. This SLY E, as you can imagine, is given by 1 over Lyn, integral of 0 plus infinity of the volume of on Z, if E is in Z, of back of Ly minus T times E dt. We have that Z dominates Y. So the formula is similar to the other one, but with respect to this line bundle Y instead of L, the respective vanishing order. But an important point is that on the numerator, we have a log discrepancy of E with respect to this pair, Y, By. So roughly speaking, this delta invariant encodes this positivity with some positivity of divisors above Y with respect to this pair, Y, By. While delta tilde, on the numerator, we just have the usual discrepancy with respect to X. So in line with the philosophy that I told before, we want to study all these notion, log stability of this notion that are encoded above y directly on x, without changing homology class, without more natural, more direct way on x. But here on the numerator, we have some expecting order that considers sections that are compatible with D. And with this, I mean that actually our sections here are respect the divisor D. So when you consider this expected vanishing order, you construct it starting from sections, and you want the section has some fixed part along D that you actually then you just actually sum. So it is a kind of quantity that I'm still studying to understand better, but the point is really that the numerator does not. You are always x, so you can compare different delta delta d for different d. Indeed, the main advantage, as I said, is this one. We can compare it, so we can study this function that send d to delta delta d, knowing that the upper level set, when this is bigger than 1, define define the existence of Kähler matrix, and the log instability, and conjecturally also the log K stability. So from this study, we have the following last theorem. Again, let L be minus Kx. Then this is uniformly K stable. This is the genuine uniformly K stability, if and only if this happens. So this is in line with some result that I got during my PhD. And the point is that studying the prescribed singularity setting may help also to understand the genuine setting. So studying the behavior of this function, so the behavior of these new stability notions, a singular guys, so a non-zero divisor D, can give information about what happens for the uniform K stability. So this is something that is varying the prescribed singularities, essentially. In my PhD, for instance, I got that studying the alpha invariant and the delta invariant, I could prove that actually delta bigger than 1 produce all possible Kähler matrix. So this is a refinement of that result. Moreover, this function is strongly continuous. So there is another topology on this set, div Lx. And this strong continuity implies that these notions are actually having this notion of stability is actually an open condition. And moreover, actually we also have obstruction to uniform K stability, studying what happened at singular guys. This is the usual delta invariant, and this is the infimum is over all possible D. So if this quantity is small enough, then the delta is smaller than 1, and you are not K stability. So there is how to say, the geometry of this delta invariant, the geometry of these notions really are encoded by this function that needs to be studied more in the future. Okay, so let me conclude here if there are no questions. Okay, thank you.